Okay, first thing I want to know, any questions on anything we've covered so far? None? All right. Now, we did the example 6 on the cycloid. Okay, we're getting ready to do the one that this figure refers to. And it says this example, the next example, establishes an important property of vector value functions that will be used in section 13.3.4 through 13.6. And that is this, the orthogonality, what does that mean? Right angles, right, okay, of R and R prime when R has a constant length. What are we talking about there? If R is a constant,
R and R prime are orthogonal?
yeah. Okay, we're talking about, what do we mean if R is constant? What kind of shape or figure are we looking at? Second? Curve, but R has to be constant, so it's not going to be varying R. It's got to be constant. Circle R, three-dimensional sphere. Okay? So, your displacement, if it's on a circle, is like that. Anything in uniform circular motion, the velocity is like that, perpendicular. Y'all know that from physics, right? Okay? Now, what it's saying even more so, spheric. As long as the constraint is the object has to stay at a constant radius, then the suggestion is the velocity of the motion is going to be perpendicular to that. So, prove that R of t, if R of t has a constant length, then R of t is orthogonal to R prime of t. Okay? So what we're saying there, the given is that R of t, the magnitude of this, constant. Okay? Constant length. Okay. What does that mean?
So it's the same.
Now,
Same magnitude.
what's that?
Same magnitude.
Same magnitude, right. Now, if that's constant, and they do something just a little strange here, but it's not too awfully strange. They don't just do the magnitude of R, which is true, but if the magnitude is constant, guess what? So is the square of the magnitude. This is an odd thing they do here. Now, if it's constant, another thing that implies is derivative of a constant is what? 0, exactly. So we can phrase that another way by saying the derivative of that constant is 0. Okay? This is, to me, the only little trick in that. Okay? Just given what you had before, it's going to be hard to come up with what you need. And you could say the derivative of the magnitude. Well, that also would be hard to come up with what you need. But the derivative of the magnitude squared, that will give us what we need. Because what would this be then? Okay. First, let's remind ourselves what R of t squared means. There is another definition for R of t squared. Yeah. Go back to, I believe it's the dot product. I don't remember which section that was. What's that? That was 12.3 maybe? 12.3, I believe it is. Let's see if I can find it. Ha! There it is. If you're in this edition, it's page 645. Theorem 1. Second?
It's a vector times itself.
What kind of time? Dotted with itself. That's it. Okay. So that's the same as, all right, d by dt of r of t dotted with r of t, right? And we know that is 0, right? Now, can you do that derivative of a product? R prime of t, R of t, plus R of t. Are you repetitive here? Okay. Okay. Well, what is that? 2 times? Okay, yeah. R prime of t, R of t. Okay? Oh, and by the way, I'm saying times. Those are dot products also because these are vectors. And we were taking the derivative of a dot product and the results will be dot products. So it's not just times, it's dot product. Okay? So, we know this. If you could read that. I'm going to spread that out a little bit, make it a little easier. Yeah, I thought I was going to spread it out. Okay, let's try that again. Yeah. Okay. Okay. 2 times r of t dotted with r prime of t. And that's equal to 0. Right? Now guess what we do next? Don't have to, but just to get rid of it, divide by 2. Okay? And now we have the dot product of r of t and r prime of t is 0. What does that tell you about them? They're orthogonal. So we just have proved what they said. That no matter what the path is, if you're on a sphere, no matter what kind of weird direction you're going, your r of t, if you're on the sphere, is constant in magnitude, changing directions like crazy. And whichever of those paths you're on, it's the r prime of t is always orthogonal. Always orthogonal to that. If this r is increasing in length or decreasing in length, the velocity has to be perpendicular. Now that velocity doesn't have to be constant. That could be changing, but it's always perpendicular. The magnitude of velocity could be changing, but the direction is always orthogonal to the direction of r of t. Does that make sense? Okay, good deal. So there was a proof of sorts, and that was example 7. Now, this is strange. The figure in my text is a really, in my text is very much simpler than that one. They took out the vast majority of the curves there inside or on the graph. I guess they found that was just too confusing, and the figure here is a little simpler looking. It's figure, 6 in both. This one has the caption that r prime of t is orthogonal to r of t if r of t is a fixed length. Okay. So that means that the velocity of that motion is always perpendicular to, or tangent to the surface of the sphere. That would be the better way of saying it. Okay, now, we've done vector derivatives. Other vector calculus would be vector integration. All right, we're going to lead up to theorem 4 here. Let's see what we can do to get to it. The integral of a vector valued function can be defined in terms of Riemann sums as in chapter 5. Okay? We'll define it more simply via component-wise integration, and the two definitions are equivalent. So in other words, here's what they're saying. if you're integrating from A to B, so this is a definite integral now, r of t dt, okay, that's the same as the integral of a vector is the vector of the integral of the components, okay? That's kind of one of those exchange type thing. So this is going to be a vector, and what will be the components of the vector? Well, the first will be the integral from A to B of x of t dt. Okay, if this r of t is x of t, which has always been y of t and z of t. I'm doing three-dimensional. Are they doing three? Yes, they are. Yeah. Okay. So this will be the integral of a vector, a three-component vector, will be the three-component vector of the integral of the components. Okay, or something like that. Okay. dt, comma, integral from a to b of y of t dt, comma, the integral from a to b of z of t dt. Close vector. Oh, I got to sneeze. No. Okay. Now, so rather, yuck. Yeah! Yeah. Yes, exactly. I gave them a little warning that I had to sneeze, but they didn't know it was coming that way. Okay. Now, they say that's equivalent to the Riemann sums. If we were trying to do Riemann sums, it would be kind of messy. You'd have to have a three-dimensional shape and then break the Riemann sums into each components, and that's why it's saying this is what it would come out being. This is much simpler to approach it that way. Because once you get it into, yeah, exactly. That I don't want to write, okay, at all. The integral exists if each of the components, x of t, y of t, and z of t, is integrable. Okay, if each of them is integrable. If any one of them isn't, then don't even try to integrate. You can't. Okay, so vector value integrals. Oh wait, I'm sorry. For example, here's an example. I think we can probably get it on this page. The integral from 0 to pi of the vector 1t sine of t dt. Okay, now using what we just said above, okay, are each of these components integrable? Yeah, certainly. So what we'll do is do the vector made up of the integral of those components. 0 to pi of 1 dx, because that is the x. Whoops, I closed too soon. Okay. Huh? First position is the x position. Okay. There we go. What's that? Okay. Oh yeah, it is t. Okay, I'm sorry. It is the x position, but it's as a function of t. It's almost a t, but it's not quite. Okay. dt. Okay. Comma. Integral from 0 to pi of t dt, comma, integral from 0 to pi of sine t dt. Close vector. Okay? This will equal t evaluated from 0 to pi, comma, t squared over 2 evaluated from 0 to pi, comma, negative cosine t evaluated from 0 to pi. Okay, close angle bracket. Okay. Second?
You said you got the zeros for it?
I'll try. Not for the last one. Okay.
Okay.
All right. I should have cleared my screen. I thought I could get it all in one line, but I probably could have if I'd have been more conservative with my writing, but I want you to be able to read it too. So we'll get these out of the way and go back to this. All right. So this will be the vector whose first component is pi. Very good. Second component is pi squared over 2. Third component is, be careful on this one. Okay. But it's minus a minus 1. Because cosine of pi is what? Negative 1. And this is the minus cosine. So that would be a plus 1.
And then plus 0, which is a positive 1, which is negative, which is a minus 1, so that's 0, right?
Well, okay. Let's do it again. Let's write it in. It's the minus, I'm going to put it in parentheses, cosine of pi minus cosine of 0. You buy that? Okay. Right? Okay. So this will be angle bracket pi squared over 2, comma. Now, minus, let's do that. In parentheses, that's a minus 1 minus 1. Yeah. Okay.
So it'd be a positive 2.
Positive 2. You got it. Okay. That's equal angle bracket pi squared over 2, comma 2. The simplest number at the end was the hardest one to get, but I guess that works out. Let's see how they did. Yeah, whoops. Did they even do it? Okay. I know I saw, oh, there it is. Yeah. Pi 1/2 pi squared, which is pi squared over 2, comma 2. Got it. Vector value integrals obey the same linearity rules as scalar valued integrals. Okay. So see exercise 72, which I think you are going to skip anyway. An antiderivative of r of t is a vector value function, capital R of t. Remember when we used to do that with f of t and capital F of t? One is the derivative or the integration of the other, antiderivative of the other, such that capital R prime is equal to little r. They're both vectors, okay? In the single variable case, the two functions f1 and f2 with the same derivative differ by a constant. Similarly, two vector value functions with the same derivatives differ by a constant vector, okay? Now, the vector does not depend on t, okay, but it's a constant vector. Now, I hope by my saying this, it doesn't make it worse. Hope you. A constant vector does not necessarily mean all the. Okay, it does mean all the components of the vector are constant, but they're not all the same. Okay, so if the x component is 3, that doesn't mean the y component has to be 3. It just has to be some constant. It could be 4/3 or negative pi or something else. The z could be something else as long as it's constant. Then you produce a constant vector, but don't think that these 3 components are the same constant. They are constants, but not the same constant. Okay, that probably didn't need to be said, but I worry that the wording here didn't specifically do that. So here's theorem 4. I think I'll blow it up. Second?
Well, I don't know. You should be.
I'm sorry?
I was going to say erase.
Oh, you can read it, okay? Well, I've already started, so I will. If R1 of t, that's a vector, and R2 of t are differentiable, okay, have to be that, and R prime 1 of t, R1 prime of t, I think I would say, is equal to R2 prime of t, does that mean these two are the same? If the derivatives are equal, does that mean these are equal? No, they just could be going in the same direction with the same magnitudes, but they don't have to be on top of each other. Okay, they could be somewhere else. They could differ by a constant vector.
Yeah, I was gonna say it could be
Right, so
different.
it could be here and
Plus
here. They're not the same, but the vector that connect them will be the constant. Yeah. For some constant vector C. And of course, this is what I was saying before. Each component of C is a constant, okay? But they're not all the same constant. You know, that's probably didn't need to be said, but it seemed like to me it's helpful. All right. The general antiderivative of the vector R of t can be written then as, and it's almost exactly what they say here. Let me do this. Clear the print. Okay. The integral of R of t dt will be some vector R of t plus some constant vector. Okay. It is a constant, and that C is equal to C1, C2, C3. And certainly those components are all constants, but they're not the same, necessarily the same constant. They could be, but in general not. Okay? They're arbitrary, that's an arbitrary constant vector. Okay. Now, the one we did above earlier, look familiar? The integral of 1t cosine t? Was that, or sine t? Sine t, okay. I thought I was thinking the wrong way there. Okay. How does this differ from what we did before?
It doesn't have.
Yeah, it's an indefinite integral, not a definite integral. Definite integral, you don't have to mess with a constant. Indefinite, you do. But we've already done the antiderivative, so anyone know what this will be? T.
T over 2 squared.
T squared over 2. Yeah, okay. Yeah, okay.
And then negative cosine t.
Negative cosine t. Now you have to do plus some constant vector C. You don't know what it is. It's arbitrary. It can have any value in the world. Okay? It could even be 0. Okay. Now, what does that mean? If this is, that's these, then the answer could be written as t plus c1, because that's just a scalar number. They like 1/2 t squared plus c2, comma, minus cosine t plus c3. Okay. Which, frankly, when you did the integration, that's what you would get. Those constants that we did before, now, it's a C1 comma. I only wrote one mark there. Okay. That, to me, is probably more useful than just doing some constants vector, is to put the constants in each of the components, understanding they're not necessarily the same constants. Okay. All right. And then finally, what we've already done, so it's sort of going backwards here, is this, the fundamental theorem of calculus for vector value functions. We just did an example when we did this. If R of t is is continuous on A to B. Now that's the requirement. The integrand, the function inside, has to be continuous. Now it seems like to me they need to say integrable, which includes continuity, but they don't include it here, so we'll just say continuous on A to B. And R of t, capital R of t, is the antiderivative of little r of t, just like we used to do. And you have the limits on it, definite integral, then this will be capital R evaluated at B minus capital R evaluated at A. You don't need the constants in because, frankly, if you had done this, that would have been the same constant for this one and that one, and when you subtract them off, they're going to be zero. You don't need to mess with them. Okay, so let's do example 8, which is probably similar to one that we already did. But let's see. Finding the position of a vector value differential equation. Vector value differential equations, plural. The path of a particle satisfies this. dr dt is equal to 1 minus 6 3t sine 3t. I knew it was in there for some reason. I didn't say it. Comma 1/5 t. Two-dimensional, not 3. Fine. Makes it a little easier. Okay? Find the particle's location. Find, that's the r of t, when t is equal to 4. So in other words, find r of 4. Okay? If r of 0 is equal to 4, 1. That particular displacement vector at time t equals 0, or t equals 0, it doesn't have to be time, but it usually is 4, 1. Okay? How would you do this?
Take the integral.
Yeah. Other words, kind of this. dr is equal to 1 minus 6 sine 3t, comma 1/5 t dt. What we did was write it in differential form, isn't it? Okay? And then we integrated. Okay? And what did we get? R of t is equal to
The integral of 1 minus 6 sine.
which is
3t.
y'all want an extra step in there?
Probably need it's just
Okay, let's do an extra step in there. The integral, the vector whose integral of 1 minus 6 sine 3t dt, comma, integral of 1, let's do the 1/5 outside, t dt, close. Okay? Is that better?
yeah,
A little bit. Ugly writing, but okay. Antiderivative of 1.
it's t
T,
minus, or well, yeah, 18.
okay. You're doing an antiderivative here, right? Antiderivative of sine is negative cosine. That's going to make it a plus. And you would have had a 6 there. I'll write it down. Cosine 3t, but then kind of the anti of the chain rule would then dividing by the 3, not multiply. If you're taking the derivative, you multiply. The antiderivative, you divide. So this goes to 2. Right? Comma 1/5 t squared over 2, so that winds up being t squared over 10, basically. Plus some constant vector Let's call it C1, C2. Got it? You buy that? Follow it? Okay. Now what we know from up here is that R of 0 is equal to, let's first plug in. What do we get there? 0 plus
1.
except the 2. Okay, 2, comma, 0. Got it? Okay, plus C1, C2. Now, it may be better if we wrote that. In fact, I think I will. I said earlier, I think it's a little bit better. Let's actually do that. I don't know what that was. Okay. All right. That's going to be 2 plus C1, comma, C2. You buy that? Oh, this would have been 0 plus C2.
And you set that equal to 4.
Ah, yes, and we know that's equal to 4, 1. So,
C1 equals 2. And
C1 equal 2 and C2 equal 1. Is that what you said? Okay. So now we know that R of t, where am I going to write this? I'll draw it down here. R of t, I'm going to rewrite it as R of t, is equal to, okay. Rather than down here, I want to save that space, okay? So R of t is going to be hang with me here for just a second. I'm going to write this t plus 2 cosine 3t plus 2, and this will be blah, 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 1/10 t squared plus 1. Okay, and now I'll erase this part. Okay, so that's my general form of R of t, and now I figure out what R of 4 is. R of 4 is equal to, getting it from here, what would that be? 4 2 times cosine of 12. Okay, plus 2, right? Comma, 16 over 10, you buy that? Plus 1, okay? I think I'll get rid of my R of 0 here because we've already used that. We've documented it. We've written it down. I hope we know what it is, and this will give us more room to write below. Okay. All right. So let's do again. R of 4 is equal to 4 plus 2 is 6 plus 2 cosine 12, comma, simplify that a little bit. Okay, I think that's a 16, isn't it? So is that 8? Oh, okay, 8/5 plus 5/5, yeah, 13/5. Okay, I couldn't hear well what you said. That's our answer. Unfortunately, it has a cosine 12 in it. If you have a calculator and get in degree mode, radian mode, be sure, and do a cosine of 12, whatever that is, you'll get a more precise answer. And 13/5, by the way, is 2.6. And so if someone can do that, 6 plus 2 cosine 12 on a calculator, be sure you're in radian mode. Okay. Yeah. Need to, just driving it around the block won't do. Okay. No, okay. Sorry. No, I'm not. Okay.
No.
6 plus 2 cosine 12. Oh, they got the same thing. So is that what you get? I see, and they got the same expression. So I hope that's a 7.69. Is it? Okay. 7.69. And this is, by the way, approximate, comma, 2.6. Okay. Good deal. All right. That finishes 13.2. Y'all want to do the preliminary questions at the bottom?
Of course.
Okay, let's see. It seems like there was another slide, though. Was there? Oh, that happens to be that particle. I didn't realize they had this. I mean, I wasn't paying attention. Now I remember they did, but I had forgotten it at the moment. Okay. This happens to be the path of that thing we just did, and when t is equal to 0, we're at 4,1, and when t is equal to 4, some time later, you're at 7.69. That looks about right. 2.6. That looks about right. Yeah. Good deal. Okay. Is that the last one? Yeah. All right. We'll probably write on this slide. State the 3 forms, I probably won't write this, of the product rule for vector valued functions. 3 forms of the product rule for vector valued functions.
So you have the regular one, right?
Okay, what do you mean by that?
The derivative first plus the derivative second.
Okay. They all follow that pattern.
Yeah.
But the clue here, there's 3 kinds of products we're dealing with.
Dot product, cross product, and then multiplication.
A scalar function times a vector. Okay. That is a product, but that's a regular. So that one would be scalar function, we'll call it f, r prime plus r f prime. Okay, just like before. Those are scalar. The f's and f primes are scalar functions. Okay, and then you're adding 2 vectors together. Then the dot product would be, let's call it u dot v. U dot v prime plus v dot u prime. Again, now you're dealing with 2 scalars, and you're adding those together because both of those dot products are scalars. Then the cross product would be u cross v would be u cross v prime plus u prime cross u prime cross v. Now that one, that one you have to be sure you keep the order. The other, you can mix the orders up on either one of those. But that one, you have to keep the order. U, if it's u cross v, it's u cross v prime plus u prime cross v. You have to have them in the right order because a change of order there negates. Okay. And if you had any doubt, look just up the page at the summary. Under product rules. Okay. And you see them right there.
That would have been
Yes, too easy. Okay. That's why I didn't mention it till now. Okay. Now, in these next 4, 2, 3, 4, 5, 6, no, next 5, indicate whether the statement is true or false, and if it is false, provide a correct statement. Yuck, okay? The derivative, let's try them without writing. The derivative of a vector, can you follow this if I don't, without seeing? The derivative of a vector valued function is defined as the limit of the difference quotient, just as in the scalar valued case. Derivative of a vector valued function is defined as the limit of the difference quotient. Now the numerator and difference would be vectors rather than scalars, just as in the scalar value case. What you think?
kind of
That sounds kind of right, and I believe it is kind of right, but let's just see if they agree with us that it's sort of right. Okay? That is indeed true. Okay? Number 3. Okay? There are 2 chain rules for vector value functions. One for the composite of 2 vector value functions and one for the composite of a vector valued and scalar valued function.
You can say no. Both. Is it just one?
Yeah, let me see. Yeah, there is just the one, and here is kind of the reason for it. Okay? Remember, your chain rule has to be, in scalar form, would be f of g of x, right?
Okay.
Now, with vector value function, you could do r of g of x. But there's no way you could do r of v of x or t or something else like that, because
A vector can't be a function of another vector?
we haven't defined anything close to that yet. So no, it has to be that. So it's only the interior one has to be a scalar. Yeah, from what we've done. So that one, I believe we said was a false. Let's see what they said it was. False. Good for them. Okay. Number 4. The terms velocity vector and tangent vector for a path r of t mean one and the same thing.
As long as r is constant. In the sphere example,
Okay.
that would be an instance of it, but other
Yeah.
than that,
Okay. Let's just take this one we've got here. Right there, that would be a tangent vector. That could be a tangent vector. That could be a tangent vector. Anything that touches there and goes, that's a tangent vector, but there's only going to be one velocity vector.
so
Okay.
that would be a no.
I think that's going to have to be a false, and the way I understand it anyway, and they say true. Okay, shame on them.
See, let's see. For a path, or
Yeah.
path.
Yeah, I guess, okay. I guess if they're defining the tangent vector to be the first derivative, if that's how they're defining not just any old tangent vector, but that's the tangent vector, yeah, that would be velocity then. Okay. I was thinking anything would be a tangent. I mean, anything tangent to that, but that's not what they're saying. Sorry about that. Okay, number 5. The derivative of a vector-valued function is the slope of the tangent line just in the scalar case. Okay. Reason why not?
Because it's still a vector.
Because what?
It's still a vector.
Okay. Well, okay. In a scalar case, it wouldn't be a vector, okay? Is that what you're saying? The false part is true. No, it is false, okay.
Derivative of a vector value function, slope tangent line, just as in the scalar case.
Here's what I think they're getting at, okay? Let's do a 3-dimensional imagination here, okay? The derivative of a 3-dimensional path, now they did say path, didn't they, or did they? That was the previous one.
That was the previous one.
Oh, okay.
Which is slope of the tangent.
Yeah. Yeah, okay. Got it. if indeed this was a surface, the derivative of that would define the slope of the tangent plane, not a tangent line. Of course, all tangent lines would be in that plane, but the derivative would define the slope of the tangent plane. I think that's what they want there.
A little too much for attention.
Right, yes, more than a tangent line can handle. Okay. And I don't think they gave the corrected, no, all they said was true and false. Okay, number 6. The derivative of the cross product is the cross product of the derivatives.
Almost.
Say again?
That would be almost.
That was an almost, huh? Is that what you said?
Yeah.
Okay.
Wouldn't it be the derivative of the first cross the regular of the second?
Right.
And vice versa on the second part. So it's kind of true, but they're not both derivatives.
Yeah, that's what they're getting at. It's not
Two
U
derivatives. It's
U prime cross V prime.
right.
It's not that. That would be the derivative, the
U
cross
prime
product.
cross V
Yeah.
and
Right.
U cross V prime.
So I think that has to be a false, but let me see. Yes. Number 6 was a false too, yeah. Okay, and number 7. This is one that will take a little writing, I think. State whether the following derivatives of vector value functions R1 and R2 are scalars or vectors. Okay, let me clear the writing off of this one. Okay. A. d by dt of R1 of t. All you have to do is state whether that's a scalar or a vector.
Oh, you do not. Isn't that a vector?
Vector, okay. B. d by dt of R1 of t dotted with R2 of t. And R1 and R2 are both vectors.
That's a scalar.
That's a scalar because the dot product of two vectors is a scalar. Derivative of a scalar is a scalar. Okay, good. Number C. Letter C. d by dt of R1 of t cross R2 of t. Hey, that's a t. Okay. Okay. What's that be? That's going to be a vector because the cross product of two vectors is a vector, always a vector, and the the derivative of a vector will be a vector. So we have there vector, scalar, vector. Good for them. All right. That finishes 13.6, except for the homework exercises, which are any of the odds 1 through 5, any of the odds 7 through 11, either 13 or 15 or both, either 17 or 19 or both, do 21, either 23 or 25 or both, do 27. Any of the odds 29 through 33, 35, or 37 or both if you choose. Any of the odds 39 to 45, any of the odds 47 to 53. And any of the odds 55 through I believe that's, I'd say 63. You can certainly do 65 if you want. That's more of a written thing and thinking through with a couple of, no, okay, yeah. So I'll leave that. You certainly can do that if you'd like. Now, if you look at number 63, you notice something is written there, prove the Bernoulli spiral, okay? Now, and that's one that you can work on if you want to, but that may also lead you to a potential paper topic Now this would be not what I usually say. What I usually say, you can write on who Bernoulli was. But on this one, you have to figure out first, which Bernoulli are they talking about, okay? Because there were two brothers, Jacob and Johann, okay? And both of them were excellent mathematicians. And then at least one of them had children, some sons, and they were excellent generally, very good mathematicians and physicists and other scientists. So I don't know which of the Bernoullis this is. Huh? So, yeah. The first you might do is find out which Bernoulli this is, and you could write on the Bernoulli family if you chose to, because they would be interesting enough too. Or figure out which Bernoulli this is and write on him, or how did he come up with this spiral, or why did he come up with this spiral, what is it used for, where is it seen in nature, or those kind of things. So
you have to do a lot of digging to write on.
yeah, not too much. I think you.
No,
oh.
literal.
Oh, was it? Oh.
To write on.
Okay. Well, I don't want you turning in any bones. I said paper. Okay. All right. Enough of that. Number 66 also mentioned torque and angular momentum. So those are a couple of other topics. If you wanted to pursue, you certainly could. And Jonathan's here. I'll find you, not blind myself in the light. Okay. We have close to half the class here. After last time we had all but one. Okay, I think we're ready for, let me see if there are any other slides in this section. No, there aren't. So let's move on to 7.3. We just finished, 13.3. We just finished 13.2, by the way, Jonathan. So we're starting on page 706 if you have the new book. Yeah, you do. Okay. So close this one out and do 13.3. Oh, yeah, okay. We're doing 13.3. Pretty sure of 13.4 is one we're going to skip. I will decide that when we get there, but 13.3 is definitely one we need to do. Okay. Start slideshow from this slide. All right. Now, in 11.2, we derive the formula for the arc length of a plane curve given the parametric form. I don't know if you remember that or not. Now we're going to talk about a three-dimensional curve. And in general, the curve is defined to be the path, R, let me get my pen back to black, okay, R of t, okay, is some x of t, y of t, z of t, okay, three-dimensional, okay. Now, where t goes between A and B, okay? Now, if that's the case, then, and let's just say this is that curve. Now, this looks like it's a plane curve, and it could be, okay? Or it could be a space curve, and we just don't have any sense of its third dimension here, because all we got is a plane to write on. But just like we did before, we will split this curve, the domain from A to B, that is the domain for t's, from A to B, split it into a partition. A is T0, and then a T1, T2, and T3 up to Tn, which is going to be our B. Okay? Now, back when we were doing the plane curves, if this was a plane curve, we estimated that plane curve by first the length of this line segment, plus that line segment, plus that line segment, plus that line segment, plus that. And guess what? You undershoot every time. If that's indeed a curve, the line is going to be a shorter distance than the curve, okay? But if you get your partition fine enough in large enough, as n's going to infinity, then that partition is going to be closer and closer approaching the actual arc length, okay? So that's called the polygonal approximation for the arc length R of t, for a t between A and B. All right. If you then have a three-dimensional curve, it's basically the same deal, okay? It's just that each of these positions here is not just position 2 variable x and y, but position of 3. So you do the same thing, okay? Now, I don't know if you remember well enough what the result of that is. But here, it basically, the two-dimensional thing was the distance formula. Guess what? The distance formula of this is basically the same thing, it's just you extend one more dimension. And if you were up into n space somewhere, you just have n dimensions on it, okay? But this is what the arc length is, the integral t going from A to B of the magnitude of those, okay, let's see. This is sort of a jump here. That's a pretty big jump, okay? You really have to go back to 11.2 or wherever it says it was and follow the thing, but this is what you came up with. Thinking of it this way, for every length there, it was a change of y, it was a change of x per change of t, which basically is your first derivative, okay? And the strange thing is, in differential form, this is exactly how it comes out being. But if you were to write this out, this x prime would be dx dt squared plus dy over dt squared plus dz over dt squared. And then you could, again, mathematicians hate when you say that, imagine you took out all those dt's, then this would cancel out, and then basically what you would have here is the square root of change of x squared plus change of y squared plus change of c squared, which is your distance formula. Remember, that would be x2 minus x1 squared minus plus y2, yeah. Each one of those, all you do is put those over dt's, which makes them derivatives, and then put a dt out here, and sure enough, you've got exactly what your integral is. Go back and see 11, that basically, maybe not quite that gross a form, but that's exactly what you wind up doing. And then you back that up, and that's exactly your r prime, the magnitude of r prime. Notice that's not r prime squared, it's r prime. And that is what your arc length is. Now, okay, I think that's enough to say about that here. That is your definition of the arc length. Where this r prime squared is the square root of the r prime magnitude of r prime is the square root of x prime squared plus y prime squared plus c prime squared. Now, I guess anymore I think would just be confusing. That's the formula. Okay, let's do example 1, I think. I'll go back and let's do it on this one. Find the arc length S, that's what we're looking for, of the helix given by R of t is equal to cosine 3t, comma sine 3t, comma 3t. Okay, for t going from 0 to 2 pi. Okay. So how would you do it? First thing you better do is get, r prime of t, which is just one derivative. We're not squaring it, we're just taking the, we're just taking the derivative now. Then we'll be squaring and stuff. What I'm doing is, what I thought you said was take the derivative of this, which is taking the derivative of that. And what would that be? Sine. Oh, sine. I thought you said 9. I'm sorry. Okay, sine 3t negative. One more thing, chain rule. Second? 3 out front, yes. Chain rule. Derivative of the outer function is negative sine, and the derivative of the inner function is 3. Okay, I thought you said 9, and I thought you were squaring it already. Sorry. Okay, comma. 3 cosine 3t. 3. Okay, and that's the same limits. Okay. Now, what your S is then is the integral from 0 to 2 pi of, and I guess that was the, I think they wanted that over that whole range, okay, or whole domain, of square root of yes, 9 sine squared 3t plus 9 cosine squared 3t plus 9 dt. What's one sort of hopefully obvious thing you might want to do with this? What's in the radical? Yeah, factor out a square root of 9, which would be a 3. Pull it all the way out, so that would be 3 times the integral of between 0 and 2 pi square root of, now what do you have left here? Sine squared 3t plus cosine squared 3t, which is sine squared 3t plus cosine squared 3t is 1. Okay, plus 9 dt. And what does that give you? 3 integral of 0 to 2 pi of, what do you call it?
3 square root of 1. Well, no, it would be
square root of 10 dt. And that would be help me. Second, you could factor out the root 10, and that would be t evaluated between 0 and 2 pi, which would be, that would be 2 pi, so this would be 6 pi, 6, yeah, I think probably 6 pi root 10 would probably be the best way to write it. That's a strange number, but 6 pi root 10, that's it. Okay. Huh? Messed something up? Oh, nope, they got it right too. Good for them. Oh, wait. No. How do they? Wait a minute. Oh, no. Well, wait.
We pulled it a 3. Should that still be a 9? It should be a plus.
Oh, you're right. That's a 1. 1 plus 1. Sorry about that. That's a 2. Yeah. Sorry about that. I forgot. We pulled out the 9. So, no. Okay. Oh, what is the problem here? It won't pull up. Well, that's why it won't pull up my eraser. It was on the wrong slide. There we go. Let's clean this up. We want to destroy the evidence to protect the guilty. Okay. All right. That was a 1, and that was a 2, and that was a 2, and that was a 2. Yeah. 6 pi root 2. I like that better than 6 root 2 pi because a glance of that might make you think the square root of 2 pi rather than the square root of 2 times pi. This removes that ambiguity, but it really doesn't matter. It's just how you write it. Okay, now speed by definition, that was, by the way, arc length. Speed by definition is the rate of change of the distance traveled with respect to the time. Okay? The rate of change of distance traveled with respect to time. Now, notice what they have in there. Distance traveled. That's not the same as your R. Your R is your displacement. The distance traveled would then be whatever path you took. If you went from here around to here, what distance did you travel? You traveled the whole circle. What displacement did you have? None. The change of displacement was none, because you started where you ended off, or ended up where you started. So this is distance traveled. Okay. To calculate speed, we define the arc length function. Okay. This other was the arc length. This is the arc length function. And I think that's on a new slide. So let's just go and let them show us what it is. Okay. Now, if you go back to the one we just did, Theorem 1, you saw the arc length was the between 2 points was the integral from the t equal a to t equal b r prime of t dt. Now what they changed here to do the arc length function is change the b to the t and then change the dummy variable here to anything else. Just not r, not s, and not t. Okay. Anything else. U is just as good as anything. B, no, not B. B would have been fine. X would have been fine. U is perfectly all right. Okay. See, it's just a dummy variable. It's getting integrated away. So this is S, the arc length, as some function of t. How far along the curve did you go? How far along that arc did you travel? That's your arc length. And this is a function of time. Okay? Whereas before, you were going just between these 2 points. How far along the arc did it take to get there? That gave you a definite interval, S. Okay? This is arc length function that along the way there, if you stop at time t, how far have you traveled? That's what this is doing. Very similar to what we had before, but now this is a function of time. Before, that was just a number. Now, since arc length is how far you traveled, your speed is then the time rate of change of that arc length. Okay? And if you think about that, I can't write it on it. Remember what the arc length was? It was an integral of, this is a function of time, it was an integral along t. So basically, the derivative undoes the integral and you're left with what the integrand was, which is r prime t. So the speed at time t is the magnitude of the velocity of line t, which is basically what we always say in physics. Okay? If you, it's a, what's that? Yeah, yeah. So getting right back to physics. Okay. Now, there's a picture that goes with that. Hopefully it's somewhat instructive. Yeah, don't do that. Okay. Okay. So let's say that here at time or t equal t0, there's your displacement vector. Okay? Now, here is the path that particle is following. At this instant, okay, the r prime is in this direction, tangent to the curve. Okay? That's the r prime at t0. Now, when you get down here at t1, you actually have a longer r, or at least in this perspective, it looks longer. This is three-dimensional, so it's sort of hard to say, but it looks like it is. It could just be getting closer to you. But that sort of makes sense because your speed was quite large here, so you expect your displacement to be increasing somehow there. Okay, not necessarily. So, but now you're doing here, so your change of this is actually decreasing here. This speed is less than it was there. Now we're taking their word for it without knowing what the values of that are, the components of that. It's going to be hard to say, but it's just showing you that even though you have a longer displacement vector, it could be the speed here is less than the speed there. Okay? And they have no basis for saying that, but they're just saying, notice the velocity vector is longer at t0 than at t1, indicating the particle is moving faster at t0 than it was at t1. Is at t1. Now, I don't know especially why they threw that in, but it certainly could be true. Okay? So let's look at example 2. Okay? Find the speed at time t equals 0, and they say s. Okay, I'm sorry. T equal to 2 seconds, and the s stands for, is the abbreviation for seconds, of a particle whose position vector is r of t is equal to t cubed I. Notice they go back and forth in which vector notation they're using, minus e to the tj plus 4tk. Okay. It says find the speed at time t equal 2 seconds of a particle whose position vector is there. Well, what might be the first thing you would choose to do? Take a derivative, usually a first guess. Okay, good first guess. Okay, and that would be what? Second? 3t squared I minus e to the tj. I did copy that right, didn't I? Now I can't even find, yeah, there it is. Yeah. I want to make sure there was e to the minus c. Okay, good. Plus 4k. Okay. Now, what would we do next? We're looking for the speed. What was the equation for speed? Oh, we got to find the magnitude of that r prime, right? Okay. And what would that be? Square root of 3t squared plus, say again? Okay, yeah, if you do magnitude, leave it, yeah, right. Yeah. Minus e to the t squared plus 16, okay. All right. Square root of 9t to the fourth. Okay, what? You're squaring that, and they're always plus, so that would be, what do you call it? E to the 2t, is that what you said? E to the 2t plus 16. Okay. So that's your speed. I hate doing this because S is arc length, and speed can't be that. So speed at time t. And what are we looking for?
What it is in 2 seconds.
Yes. At how many? 2 seconds. So the speed at 2 seconds would then be the square root of
Plus 2. 16.
Yep. E to the fourth plus 16. All right. Oh boy. That basically comes out being 10 times 16, right? 9 times 16 plus 1 times 16 would be 10 times 16, right? Okay, so that'd be 160, square root of 160 plus e to the fourth. And unfortunately, I don't think there's much else we can do with that except pull out the calculators and give me an approximate answer for that. Now, they did it slightly differently, but I think you come out the same thing. Let's see what you get. A little louder. 14 point. 214. Huh? Okay, wait. Okay, 160 plus e to the fourth. Then you took a square root of it? Or did you take the square root? Okay. Okay. Beginning to scare me. Yes. In the book, they got 0.65. Is that okay? And that would be in feet per second. Did they give you units? They gave you seconds, but I know, but I never saw them to give you the R, what that was in. So they just made up the feet part. So it was something per second, but I guess they assumed it was feet.
So units per second.
Yeah. Whose position was, they should have said R in feet. That would have been it. All right, good deal. Now, we move to a concept called the arc length parameterization. How are we doing on time, by the way?
2 minutes.
Is what?
2 minutes.
2 minutes to go? We're not going to get very far on arc length parameterization, I don't think. Okay? Yeah. So we'll start there next time. And in honor of finishing early, let's do some extra homework exercises. Okay. Do any of the odds 1 through 7. Do 9. And do any of the odds 11 through 15. Let me see. I think you can do 17 and or 19 and stop there, I believe. I believe you can do 17 and or 19. Okay. All right, good deal. 13.4 is relatively short section, and we'll finish that next time. 13.3. 13.4 we are doing. I couldn't remember exactly. I think it was in my other class we were going to skip a section. 13.5 we certainly will do. And we won't do 13.6. It's great stuff, but we'll probably skip that one. Yeah, that's it. Huh?
When's the test?
When it's what?
The test due.
Whenever you finish it, but try to turn it in before we're ready for the next test.
Okay.
Because I'd like to give them back to you beforehand. Okay.
Awesome. At a team meeting. Yeah.
Yes. Yes.
Right now.
Okay. Let me end this.